Okay, so here we are. We're going to talk about exponential growth and decay today, and we're going to start off with deriving the formula for that you see up at the top here, and you'll notice I've changed it. So in exponential growth and decay, we'll come back and talk about what all these different variables mean, but we have a formula, and this formula can be derived from this differential equation down below. This is a calculus formula, and this formula is basically a quantity y, and that's the y that you see on the right side over there, whose rate of change, there's dy dt, over time is proportional to the amount present. So the rate dy dt is proportional to some value of k times y, where k is some constant in the function. Okay, so we'll talk more about that constant later on. So we're going to start off, and we're going to separate our variables here and show what this comes up with. And so we're going to multiply both sides by 1 over y to get rid of the y on the right side. We're going to leave the k over there, and at the same time we'll go ahead and multiply both sides by dt. Okay, so hopefully that's obvious what we're doing there, but we're going to end up with 1 over y dy equals k dt. And again, remember, k is just a constant, it's not a variable here, so we separated our variables here. And once we have our variables separated, we're going to take the integral of each side. So the integral of 1 over y dy will equal the integral of k dt. And again, k is not your variable, t is your variable, time. So if we integrate both sides, take an antiderivative, we get the natural log of the absolute value of y on the left, and we would get k times t plus c on the right side. Okay, so the antiderivative of k would be k times t, because t is the variable there. To solve for y here, we want to raise each side. We're going to exponentiate. We're going to raise each side. Ln of the absolute value of y and e to the kt plus c, the whole side being raised with a base of e. Now, if we look at the left side, e to the ln absolute value of y would be the absolute value of y, but I'm not going to put the absolute value on there. And the reason I'm not is because if you look at the right side here, no matter what t is, no matter what c is, no matter what k is, this right-hand side will always be positive. So e raised to any power is always going to be positive, so we don't need the absolute value on the y anymore. And so we would say that this side is e to the k times t plus c. And we can actually keep simplifying a little bit. So we can take that right-hand side and we can rewrite the right-hand side as e to the kt times e to the c, and all I'm doing is using some exponent rules here. We know that in exponent rules we can do, I'm going to come over to the left side here, a to the m plus a to the z, a to the m times a to the z. We know that that's just a to the m plus z. So all I'm doing is using that rule in reverse. On the right hand side here, I've got e to the kt plus c, and I split that up. And then I'm going to rearrange a little bit more here. Since e to the c is just some sort of a value, a number, I'm going to put that out front, and so that would be times e to the kt. And then e to the c, like I said, it's just a number again, so we can actually take that and rewrite this, because it is just some constant, we can rewrite as y equals c times e to the kt. Okay, now in this function here, all right, let me scroll up a little bit here. If I let t equal 0 here, okay, and just bear with me here for a minute. So if we let t equal 0, we would get y equals c times e to the k times 0. Well, k times 0 is 0, and e to the 0 is just 1, so we would get a y value that's equal to c. All right, so what we're going to do here is we're going to let this y value because this y value is different depending on the value of t that we plug in. So if I plug in t equals 0, I get y equals c. If I plug in t equals 1, I'm going to get a different y value. So the initial y value up here in the original equation is not necessarily the same as this our y value in the initial equation. After I plug in a value of t, I end up with another value right here, some other value. We're going to call that our ending value, or our amount at the end, something along those lines. Okay, so that c value there, we're going to let that c value equal, and we're going to call it y sub 0. Okay, so that's going to be our y sub 0. And it's the same thing if we were to write y of 0 equals c times e to the k times 0. Same type of idea here. We're just using subscripts instead. All right, and so we end up with this equation, and that's going to be y equals y sub 0 times e to the k times t. All right, and this may look familiar to something you saw in Algebra 2, but in Algebra 2 it was written like this: a equals a sub 0 times e to the k times t. Okay, so what do all of those things mean? So I'm going to come back over here to the left side. I'm going to rewrite this equation because the k and the t are supposed to be exponents here. So a sub 0 times e to the power of k times t. Okay, so what is a sub 0? A sub 0 is your initial amount. Initial amount. And t is the time, so that would have to be a positive value. A is the amount at end. Amount at end. And that's at the end of the time, at end of time. Okay, so whatever time period that is, maybe I should say amount at end of time period. Okay, k is what we call a constant. It's sometimes called the constant of proportionality. Constant. And so you'll probably hear it listed as that, so I'm going to write it: constant of proportionality. And basically what k determines is whether you have k determines growth or decay. Growth or decay. Okay, and so if you look at the equation, obviously your a value, your initial amount, will most likely be a positive value, some amount of some kind. So this guy here is always going to be something positive. And then your e value, e to the k times t, that's always going to be positive as well. So a sub 0 is positive, this is positive. So even if k turns out to be negative, all of this still is a positive value. But what you end up with is, if k is negative, you end up with exponential decay. Exponential decay. And if k is positive, you end up with exponential growth. Okay? And, just a little refresher on what those look like. Exponential growth would be a graph that looks like this. Okay, it grows as time goes on. Exponential decay, on the other hand, looks like this. It gets smaller as time gets bigger and bigger. Okay, so what we're going to look at today are some examples of exponential growth and decay using that formula right there. All right. So example number 1 says the number of bacteria present when the experiment began was 1,200. After 100 hours, there were 2,700 bacteria present. Assume exponential growth and find the time required for the number of bacteria to increase to 30,000. So our initial amount, our a sub 0, was 1,200. That's never going to change. The initial amount never changes. The time, it says after 100 hours, so after 100 hours, there were 2,700 bacteria present. So you remember, the time always goes with an ending amount. So 2,700. And then it says, assume exponential growth and find the time required for the number of bacteria to increase to 30,000. Well, so now they're wanting me to find a t value, so some value of t, when the a value would equal 30,000, or the amount at the end would equal 30,000. So we're looking for a t, but we also don't have a k. And in order to do this, we need k first. All right, so I'm going to go back to my equation that we talked about on the other side, and I'm going to start off, and I'm just going to look at that. A equals a sub 0 times e to the k times t. Now, the only way I can solve for k first is if I can plug in something for every other variable in here. So I've got three variables. I've got a sub 0, and I've got t. E, remember, is just a number. So a, what I'm going to do is I'm going to use all the stuff in the blue on the left side over here, because I have an a value, I have a t value, and I have an a sub 0 value. So I'm going to plug those in, and I'm going to do 2,700 equals a sub 0, which is 1,200, times e to the power of k, and my t value there is 100. So I'm going to start off by dividing both sides by 1,200. Okay, and I'm going to try not to round anything off here, because I can do some canceling with my zeros here. 27 and 12, I can divide both of those by 3, so that's going to be 9/4 over here, I believe, if I did that correctly. And on the right side, I've got e to the 100k. In order to solve for k, I need to log both sides. So log of 9/4 equals the log of e to the 100k. And hopefully you're already thinking, okay, the right side, well, let's leave the left side alone here. Let me rewrite that. So the right side, ln of e to the 100k is just 100k. And then I can divide both sides by 100. So I'd have the natural log of 9/4, that whole thing divided by 100, and that would equal my value of k. Now, I could pop that in my calculator and get a decimal value for that, but I don't need to do that yet. What I'm going to do is I'm going to bring this guy up over here. Actually, I'm going to come back up on the right side, and now I'm going to look at this 30,000 right here. So now I'm talking about all the data that's in red on the left side of the page there. So I'm going to go back to my original formula, and I'm looking for an a value at 30,000 now. So I'm going to do the same thing over here, only with 30,000. And this is going to equal the initial value, 1,200. So again, that didn't change. Times e to the power of k times t. Now here's the thing. Actually, I can erase the t. Oh, no, I can't. I can't. So this is e to the k times t. Now, I need to solve this again. Now, I do know what k is equal to. I know that k is equal to all of this, but I don't feel like putting all of that in for that exponent. So I'm just going to leave k there until I get out my calculator. So I'm going to divide out the 1,200 just like we did before. So we'll go ahead and do that. Get rid of that. Cancel off some zeros here again. So we've got 300 over 12. If you divide that, that's 25. Equals e to the k times t. So remember, this time we're solving for t. So I'm going to log both sides again. The log of 25 equals the log of e to the k times t. And so now I've got the ln and the e cancel each other out. So now I've got natural log of 25 equals k times t. And I can divide both sides by k. So t is going to equal the natural log of 25 divided by k. Now, when I go to punch this into my calculator, I'm going to take and put in my value of k over here. So for this first time, I'm actually going to write out what we're going to punch in. So we're going to do t equals the natural log of 25 divided by the natural log of 9/4. You're going to have to be very careful about this. Divided by 100. Okay? So you want to practice popping that in your calculator, and you should end up with 396.936. And remember, we're solving for t, which is time. Our time was given in hours. Okay? So it'll take a little under 400 hours until there's 30,000 bacteria here. Okay? So number 2, in a certain research experience, the population of fruit flies increases according to the law of exponential growth. If there were 18 flies after the second day of the experiment and 300 flies after the 4th day, how many flies were in the original population? So the original population is A sub 0. Okay, so let's look at the rest of the information. We had 18 flies after the second day. So at t equals 2, okay, so I'm just going to use this, t equals 2, that 2 goes with 18. And then we had 300 flies after the 4th day, so at t equals 300, that value is going to go with, oops, excuse me, not t equals 300. Let's see, the second day, that's going to be the 4th day, so t equals 4. That's going to be 300. Okay, so I'm given 2 t values, 2 a values, and they want me to find a sub 0. Well, again, I need k first. So we're going to have to find, oops, we're going to have to find k before we can do anything else. Need k. So going back to our original statement again, our original formula, a equals a sub 0 times e to the kt. So this time, instead of plugging in for a sub 0, I need to solve for a sub 0. So we are going to use, excuse me, hang on. All right, we're back. So in the first one, we had enough information so that we could plug in for t, a, and a sub 0, and then we could solve for k. The problem here is we've got 4 variables and we only have 2 pieces of information that we can plug in. We can either plug in 2 with 18 or 4 with 300. So I'm just going to write both of those out and we're going to see what we're looking at here. So the first time the a value was 18. We didn't know what a sub 0 was. E, and then we had k times 2. On the next one, we had 300 equals a sub 0 times e to the k times 4. So you can see we've got too many variables there. But what we can do is we can solve both of these for a and then use those to solve for k. So I'm going to divide out e to the 4k on both sides of the right one here, e to the 4k. Do the same thing over here, e to the 4k. So I've got on the right, I've got a sub 0 equals 300 over e to the 4k. I'll do the same thing on the left side. I'm going to divide out e to the 2k and e to the 2k. So I've got 18 over e to the 2k equals a sub 0. Now, since both of them are equal to a sub 0, then we can set them both equal to each other as well. So I'm just trying to figure out where I want to do this. So I'm going to take 18 over e to the 2k, and I'm going to set it equal to 300 over e to the 4k. Now, in order for me to solve for k, I've got to get the k's on one side, so I'm going to take this equation right here, and I'm going to multiply both sides by e to the 4k. So that's going to give me 18 e to the 4k over e to the 2k equals 300. I can go ahead and divide both sides by 18. So the right side is going to be 300 divided by 18. And we'll simplify that later. We're going to worry about it later. But on the left side, I've got e to the 4k over e to the 2k. This is an exponent rule. Whenever you're dividing bases that are the same, you can subtract the exponents. So the left side of this is e to the 4k minus 2k, which again just leaves me e to the 2k. And if e to the 2k is equal to 300 over 18, all I've got to do now is finish solving for k. So I'm going to log both sides again. The log of e to the 2k is equal to the log of 300 over 18. On the left side, the ln and the e cancel, so that's 2k equals ln of 300 over 18. And then I divide out the 2 on both sides. So I get k equals the natural log of 300 divided by 18. And you could divide that whole thing by 2, or I can just say 1/2 in front of the log. So that's another option if you'd rather not mess with some complex fractions there. Okay? So that's another way to do that. So once we know k, now we can go back to our original focus here, which was finding the initial amount. So I'm going to come back over to the left side here, and we'll finish working on this one. So my initial amount, in order to do this, I can use either the information from the 4th day, or I can use the information from the 2nd day. I'm going to use the 2nd day just because the numbers are smaller, a little easier to work with. And so I'm going to come back over here, and I'm going to choose 18 equals a sub 0 times e to the k times t. And again, keep in mind here, actually the t value should be 2 here, so k times 2. And my my k value is this value that we just found on the right side. So we'll plug that in later. So I need to get rid of the e to the k times 2. So this is we're gonna divide that out. This is gonna be 18 over e to the 2k equals a sub 0. And now again, I would just pop all of that into my calculator, and I'll write it out again just so it makes sense, hopefully. So this would be 18 over e to the 2 times 1/2 ln of 300 over 18 that we got from the right side, and that is equal to a sub 0. All right. And you know what? Actually, I'm going to come back to this one just for a second here, because you can pop that in your calculator, but you can also do a little something else here. So think about, if you multiply, first of all, if you go back down to the bottom of this fraction over here on the left, 2 times 1/2 is just going to be 1. So really all I'm looking at here is 18 over e to the ln of 300 over 18. Well, think about this. Remember, this is a sub 0, right? Well, the 18 in the top, I'm not going to mess with that. But look at the denominator here. E raised to a natural log. Just like the natural log of e cancels out, e to the natural log also cancels out, and that 300 over 18, we can bring that down as the denominator underneath 18. So if you were to punch into your calculator e to the ln of 300 over 18, it's going to spit out 300 over 18. So now we take this, and remember this is a sub 0. So now if I were to flip that over and multiply, I would have a sub 0 equals 18. Flipping over the bottom, that would be times 18 over 300. And however you want to simplify that, actually I've got it over here on the 300, is going to give me 1.08, which would equal 1 fly. Okay, so example number 3 here says that y represent the mass of a particular radioactive element whose half-life is 25 years. In other words, if we began with 1 gram of the element, only half a gram would remain after 25 years, a quarter of the gram after 50 years, and so on and so forth. How much of a 1 gram mass would remain after 15 years? Okay. And it looks like I've got two things going on here. Good gosh, these notes are all messed up, so I got to get rid of this. Hopefully your notes don't say that, but I have a bad feeling that they do. All right, well, we'll keep going with this first one. How much of the 1 gram mass would remain? Well, that means that my initial amount is going to be 1 gram. All right. I know that after 25 years, okay, 25 years, I would have a half a gram remaining. That's what half-life does. My goal here is to find out in 15 years how much of that is remaining. Okay, so again, you can see on the left side I've got 3 of the 4 variables in blue that I can fill into the equation. So I'm going to use those to solve for k again. All right, so I'm going back to a equals a sub 0 times e to the kt. And so my a value is going to be 1/2 equals a sub 0, which is 1, times e to the k times t, so t is 25. Well, dividing by 1 on both sides doesn't change this thing, so it's just a half equals e to the 25k. We'll take the log of both sides. Log of 1/2 equals the log of e to the 25k. So I'm left on the left side with log of 1/2. On the right side, I'm left with 25k, and I can divide out the 25. So I have a log of 1/2 divided by 25 equal to k. Now again, there's no reason to take out your calculator here yet. Now what we want to do is go back and plug in and see if we can solve for 15 years. So now I know that my amount at the end, my a value, is just going to be a. My initial amount is still 1 times e to the k times, and this time the t value is going to be 15. Now this one I'm pretty much done, because I'm going to take k, I'm going to pop it in to my calculator right here, and I'm going to end up with a equals, and of course I didn't pop that into my calculator, so I don't have a number for you. Oh yeah, maybe I did here. 0.660 grams would remain after the 15 years here. Okay? All right. Last one coming up here. Oops. And that's the one that disappeared on us here. Interesting. Okay. Well, we're going to bring this example down here. Let's see if we can do this down here. It says, if the half-life of dysaperium is 15.8 minutes, what percent of the amount present now will be remaining after 1 hour? Okay, so there's a couple of different ways we could do this, but and I did this first one using 1 for the initial amount and 1/2 for the amount at the end. You can also do this with percents. So it says, what percent of the amount present now? Well, what's the amount present now? That's 100%, right? So my initial amount, my a sub 0, could be 1, or it could also be 100%. Okay? It says that the half-life is 15.8 minutes. So at time t equals 15.8 minutes, I know that I would have an amount left over of 50%. Why am I doing this one with percents instead of numbers like I did in the previous one? Because it asks about percents. Okay, and the number 1 really is 100% if you move the decimal over. Okay, so they want to know how much will be remaining after 1 hour. So that 1 hour is actually 60 minutes. So my initial amount's not going to change. What's going to change here is my time is going to equal 60 minutes. and I want to know the amount after 60 minutes. And because I'm using percents in the red, my amount will come out as a percent. All right, so let's plug in and see what we got. All right, so I'm going to do 100, excuse me, 50%, that's my amount after the half-life, equals the initial amount, 100%, times e to the power of k times t. So if I divide out the 100 on both sides, you can see I still get a half, equals e to the k times t. Oops, and did I put in t? I should have put in 15.8, shouldn't I? K times 15.8. All right, so I'm going to rewrite this side, e to the 15.8 k. If I take the log of both sides, I get the natural log of a half equals 15.8 k, because remember, natural log of e was going to cancel. And then you can divide out the 15.8. So I have natural log of a half divided by 15.8 equals k. All right, so now that I've got that, I can just go back and plug in 60 minutes and solve for a. So I've got a equals, and this time it's going to be the initial amount, 100%. Okay, so this is where the difference is going to come in when I go to solve this, times e to the power of k, and then t in this case is 60. So remember, our k value is going to come from right over here. Okay, and we're going to pop that in the calculator, and this one I don't have a number for, so I'm going to crank this out real quick. This is going to be 100 times e, and we're going to raise this to the power of, okay, so I got to be careful here, 60 times the natural log of 1/2, and then we're going to divide that by 15.8. So this turns out to be 7.192, and something doesn't seem right there. You know what? Let me check my answer here. I'm doing this kind of fast. I don't want to screw this up. No, I think my answer is good here. So it's 7.192%. At first I thought that number was a little bit low, but then I realized, okay, you know, if you have 100% initially, then after one half-life, which is 15.8 minutes, okay, so 100% at time equals 0. After 15.8 minutes, you'd have 50% left over. So if I double 15.8, that's 31.6. So after 31.6 minutes, I'd have 25% left over. And then if I add another 15.8, I get 47.4 minutes. I would have 12.5% left. And so I'm close to an hour here, so I'm not quite at the fourth half-life. So if we were to add another 16 minutes here, 15.8, we'd end up with 2 and 5 and 7 is 12, 13. So 63.2 minutes. So that's a little over an hour. We'd be at 6.25% of the amount remaining. And so we're just a little over 6.25%, which makes sense with what we're looking at here. All right. So hopefully that made sense, and I apologize for the one example in the middle there. Hopefully I didn't screw you up too much on that. All right. We'll see you later.